Okay, so thank you all for joining, and thank you, Rajiv, for accepting the invitation. It's quite early for you there, so thank you for joining us here to present. And so I would like to introduce you today here, Rajiv, who is our speaker. Rajiv is the director and head of process optimization at Ausenco, and he has more than 23 years of experience with SAG-based circuits, HPGR mind-to-mill integration, and AI-driven analytics. And Rajiv has over 50 peer-reviewed publications. So it's a great pleasure for us to have Rajiv here today to present the work, practical framework for debottlenecking underperforming comminution circuits. So thank you, Rajiv. You have 40 to 45 minutes to present, and then we can have some time for some discussions. It's over to you. Thank you.
Thanks, Julia, and welcome everyone. It's a pleasure to present to everyone. Currently I'm in Vancouver. It's 5 a.m., so I had to speak softly as my family's still asleep. So this presentation is something which I provided, something similar to which I provided back in 2021 as a masterclass to the CMP, the Canadian Minerals Processing Conference. I think it was in 2021. I thought it was back then we presented the framework and we provided methodology, and I thought it would be a good forum to present that bits and pieces from that previous masterclass, because it still holds true every time I go to a site and the approach we take. To begin, so I provided a wordy abstract. So I summarized the abstract into key focus areas. So we're talking about a systematic data-driven debottlenecking, looking at a structured framework using simulation, benchmarking, analytics. And the overall purpose here is to quickly identify the opportunities and define a pathway. And once you define a pathway and then you establish part of that pathway is to establish a baseline. There are metrics in comminution. We particularly look at throughput or grind size or recovery, and how do those levers adjust to define the overall value we want to gain out of this exercise. And lastly, whatever solution we're providing needs to be sustainable. And we need to provide a clear pathway what that solution is going to be. And this is what this presentation is all about. So generally, this is more of a general discussion. So poor plant performance is a result of lack of understanding the process, poor benchmarking, not challenging the norm, or poor control. And those 4 points have been consistent in all my experience. Every time I go to an operating site, it's one of those or a combination of those. That's what's resulting in poor performance. So the general approach here to debottlenecking, optimizing comminution circuits in particular, is going back to the basics. Is the process control set up properly? Is your mill being charged correctly or frequently charged? If you're operating, understanding the constraints. So as your constraints shift from the SAG to the ball mill, now the ball mill becomes a constraint. So how we can optimize the ball mill? And what are the levers we can adjust to maintain a stable and optimized comminution circuit? The third point there, focusing on stability. I think that's very important. Every time I go to a site and talking to people and review the process control, you see an unstable system, and it's very difficult to optimize. So the first objective here is to stabilize the control of the system. And so once you stabilize it, then you have a clear target to push or elevate the system to more optimized state or more a stabilized objective. And lastly, it's about pushing the limits of the assets. So once you understand where your opportunities are and what are the lead, how well we can push the segment in terms of power draw, that's the main objective. So what are the limits? Mechanical limits, electrical limits, and what are the operating parameters we need to reinforce in terms of the operating strategy. We don't break the equipment, but we can just make sure that we operate the equipment safely and within the operating limits. So that gives you an overall general view, talking about the poor plant performance and the debottlenecking strategy generally we take. So step one, define the value. So I've provided here more of a business framework, and that's very important when you start looking at optimizing the strategy or a pathway. The solution needs to be defined from a value perspective. So I'm used rugby in this case. So in rugby, the objective of the game is not to run up and down the pitch, but to score points. The object of the business is not to create plans, but to spend money and generate profit and value. So generally, sorry, I'm just having a bit of feedback here. Is Julio?
Yes.
I think someone's muted. Okay, no worries. I just had a bit of feedback on my headphone. So the third point there is generating value depends on less on performing tasks, does on completing the right jobs effectively. So that's what it essentially is. Now you can find a good solution, but is it the right solution? And is it going to add the biggest value to the overall business? So once you define a business framework, you can build a bit. I'm sorry, there's a bit of a typo here, but building a business case. So return on investment, looking at cash flow, value, and risks. Generally, return on investment, it's all about revenue, increasing revenue, reducing operating expense, and increasing value and reducing risk. So when you're particularly looking at revenue, the product, the general lever we can, particularly in the combination circuit, we can adjust its throughput. Peak rate is pretty much fixed, and recovery, that's largely in the flotation circuit, but the lever here is going to be grind size and equipment availability. And this green highlighted section, your operating expenses, generally, if you're pushing the limits of your asset, or particularly SAG or crushing circuit, you are going to increase the frequency of the relining schedule. Therefore, your utilization reduces, and therefore your overall equipment availability reduces. And that has a big impact on achieving the throughput. And so you just need to understand where your opportunities lie in terms of adjusting to maximize your return on investment. So this is just highlighting the linking value. So particularly here to talk about combination and optimizing combination circuit. I mean, there's opportunities looking at mine-to-mill, optimizing the blast, looking at your geometallurgy, providing the best feed to the grinding circuit. They talked about reducing operational cost, increasing availability, utilization, and it's also understanding the limits of your equipment, deep capacities. What's the maximum capacity we can push that? I mean, there's a design capacity, but you're also understanding what is the maximum capacity we can push that equipment. And lastly, all of this equates to a value, which is efficiency or it minimized dollar per ton of product. I've we started looking at greenhouse gas emissions as a dollar per ton as a metric because more and more clients are interested in as a measure of performance. And so we look at particularly if you're going to increase your grinding media consumption, that's going to have a big impact on your greenhouse gas emissions at the scope 3 level. This slide here talks about the theory of constraint. So when the approach we take, there's a book by Eli Goldratt, I believe, and he talks about the theory of constraints, and we apply a similar methodology, is to identify what the constraint is. For example, the signal is a throughput limiting equipment, and how do we exploit it? So that means making sure that equipment is fully utilized, maximize power draw, make it more efficient. And part of that workflow is subordinating the operation. So for example, if your equipment is the constraint, for example, the sag mill, can we reduce the feed size, increasing the fragmentation through finer blasting. But that means that you may have a constraint downstream. You're now pushing throughput through the sag mill. Your flotation circuit becomes a constraint. Your tailings pump becomes a constraint. So you just need to understand it, not just the comminution circuit, what the overall system and how the constraint shifts from feed to the sag mill and post sag mill product. Once you understand that, it's all about defining a workflow, how we're going to achieve and exploit the opportunities. For example, redesigning liners, installing secondary crushing, etc. And then once you've done all that work, and you have to go and reassess it, make sure that what you've defined in terms of opportunity is achieving the objective. So this section, I'll just quickly go through some of the analysis we use and we developed over the years. So this is just going through the stages of diagnosis, and on the right side here, I've prompted some focusing questions. So I think the most important aspect of doing this type of work is collaboration and communication with the key stakeholders, and asking the right questions, and what are the overall objective. And then we go through a phase of what data is available, what information is available. Not all information is useful, but how can we collect, and what are the gaps in the data and the analysis, and what is needed going forward. The investigation stage is also through surveying and sampling, looking at targeted test work, and that's can be done through trials at site, and then out of those trials, and we'll understand how the system works, and we provide a new opportunity and a clear pathway. And it is all about understanding what we know and how we work through the problem. And lastly, it's all about defining a priority, from immediate fixes, from process control to major projects, and what is that pathway in the next 3 to 6 to the next 12 months. So this gives you an overall view on the approach we take, and the key focusing questions we define as we work through the problem. In terms of process simulations, I'll put a comment here. Simulations are tools to define the opportunity or a guide to understand the process. And then we use several. I mean, there's Excel-based metallurgical models, Syscad models, GCC, and largely what we use are steady-state type of simulators. The background here is a Excel-based simulator. I think I developed 10 years ago for the here. It's a complete mine to mill, looking at the crushing circuit, 3 grinding circuit. We had a flotation, and we also had a bypass to the pre-leach, and then it goes to pressure oxidation. And the overall objective here in this simulator was to understand where the constraints are based on different fragmentation and size distribution from the plasma practices. But the purpose here was to provide a guidance in and what levers we need to adjust to provide to the operating team or the metallurgist at site to change their practices. And the process simulation typically we use as a guide to define what the issues are, and it's now it is a good tool. I mean, as I mentioned, yeah, Syscad is widely used now, and we've incorporated some of the models into Syscad. And yeah, so general view here is baselining against design and benchmarking using plant data or survey data. I'll put this chart here. So this is a chart I developed with a process control guy who used to work for me, Carl, back in 2020. And this chart is about understanding stability. Most of the time, we're dealing with a system which is unstable and highly variable, and it's not even close to the constraint. So the target is much lower, and you got a big distribution in the noise. And as you calibrate and tune the system, the noise distribution reduces. Now you can now increase that target close to the constraint. And as you start to incorporate advanced process control or modern predictive, you can even elevate it further and further close to the constraint. Most of the time, when we're dealing with optimization, it's either this stage here, base case unstable, or let's say a system which needs to be upgraded or finely tuned. I see there are more and more clients interested in AI and real-time optimization, which, yeah, I mean, that's the future and the vision. But first step is to make sure the system is stable and instrumentation is working before you can consider to install an advanced process control machine learning system. So these are some of the tools and diagnostic workflow we developed over the years. I like visual things, and what we've done here is taken the operating data and we created heat maps. And what that does is that visually you can see this, how stable and how unstable, or rather unstable, the equipment's performing. This is a SAGMO looking at 24 hours with the process instrumentation data. I've got a 6-month worth of data and a yearly data. And you can see the distribution. So the heat map gives you how stable the system is operating, and the color grading gives you the operating band. And also you can pick out zones. For example, over here, over a period of year, you got 2 zones where the load's operating at. So we just need to understand why the load's changing, and what's causing that load to change, and why the operators, and what's that consequence in terms of SAGMO performance on throughput particularly. This case here for a SAGMO discharge density in the highly variable, and what's causing that, and why is it not stable? And that gives you an opportunity to identify what the key focus areas should be. This chart on the right here, what I like to do is take the process instrumentation of the Pi data, and I filter them by going from low throughput to high throughput. And I can see the performance of the load, the speed how it changes, and the mill noise, particularly if you have an acoustic sensor installed. And you can see as your for low throughput scenarios, how the SAG was performing and how the load's being stabilized. And that gives you a quick overview of how stable the system or the control system is reacting. Or you can pick out any unusual control set points in which you can mitigate or trial or fix. This is a job we did in Africa, I think it was about 5 years ago. You know, so typically, what you should see, a mill load should be stable for variable speed of drive, but the way the sag mill has been operated, they try and fix the sag mill speed. And what that does is they change the mill load set point and to maximize power draw. Ideally, what you want to do is change the mill speed to stabilize the mill load. And what we did here was so we got a sag mill weight tons mill load, and we try and reduce the distribution, make the distribution tight in the control. And what that did was actually push throughput because we stabilized the system roughly by 5%. And this method, when we use color maps or heat maps, are very useful way of analyzing data. And what we've done is actually using these color maps, we started to train some of our machine learning models because it's easier to pick out color and variance in color in the data rather than just looking at numbers. And it's an ongoing project with some of my guys to look at, particularly around how stable the mill load is or how what the distribution of the mill speed for variable speed, variably speed, variably variable speed operation in a sag mill. This table here is understanding the constraints. So, for example, in a sag mill, we got immediate levers such as increasing the volt charge. There's opportunities to change the liner design, but it's not just that. It is understanding the grade system, the pulp system, what's the capacity, and then looking at the rotating parts. As you starting to push sag mill to its limit, you need to understand how much load the mill show can take. So you need to, typically that's provided by the manufacturer, or you need to undertake this finite element modeling by specialists. Rotating parts like the gears and the pinions and all the mechanical parts of the mill. We just need to understand it can achieve the fairly consistent operation at the higher power draws. And not just mechanical, we need to evaluate the motors, the motor winding temperatures. They all become constraints. For example, if you've got a mill motor installed in, say, Asia or where temperature during daytime can be fairly high, you need to make sure that got adequate cooling. So it's just not about the process. It's all about understanding the mechanical limits and the electrical component limits. So step 3, just to walk through the implementation plan. Generally, we follow 3 core principles. It's being proactive. We do through action, and we try and reduce complexity. Some of the basic things, charging ball mill, make sure you're operating at the correct set point. Essentially, it's doing the essential things better. That's our 3 core principles. And I've got here, I'm sure you've seen Greg present that. It's all about communication again, listening, aligning, and trying to build trust with the site team. And ultimately, we need to deliver what we set out as an objective. And these are what I presented here is finding a solution is easy. It's communicating and executing is very, very challenging. Particularly, you're working across not just immediate line contact, could be a metallurgist or a plant operator. You need to work across your maintenance manager, your mill superintendent. They all need to come to the table and understand what we're trying to achieve with our objectives, and it needs to be communicated clearly. Um, this table here is providing a general strategy and implementation. So when you're looking at mine to mill, in terms of strategy or process control, there are different pathways we can take. And for example, if your implementation is going to be mine planning, change operations management, that's more looking at optimizing the resource definition, which probably that means you need to build a technical model, trying to define for changing feed type, grade, and what that impact will have in the overall opportunity. And if you're taking a debottlenecking pathway, typically you want to have a technical economic model and understand the supply chain or maintenance management. So this gives an overall view on the execution strategy we take, and it's not defined, but it's a first step to developing a plan. And once you identify the opportunities, and what we do is rank them, and in terms of quick wins, small projects, and major projects. So quick wins are generally immediate changes, process control, operating practices, set points, where pretty much no capital needed or required. It's just physical changes at site. Small projects are usually minor modifications, a pump upgrade or a chute upgrade. And then we're looking across here, major projects in terms of value, which requires a lot of effort. Could be addition of a second crushing circuit, a new prime crusher, or tertiary grinding if required, as you want to achieve a finer grind. And what that means is that now you'll have several options, and where part of that journey will be to undertake trials. And but the trial will discard an idea, which option, say, for example, option 3, but we'll take further stress tests. Stress test is when you push the equipment or the comminution circuit to the limit, and you understand, okay, these are the constraints, so you may need to upgrade the liners, and that or change the sag mill discharge trommel that has become a constraint. And we refine that opportunity, and we undertake a second stress test. And that value changes over time, and these options have to change as well and accordingly. So, for example, option 1 seems like a feasible option, but it has to be understood and changed. And seeing it through, lastly, I think just to summarize, it's all about having a clear strategic direction, defining the value, supported through thorough analysis and accurate data, rigorous methodologies, understanding the process upon which the business relies, provide tools to monitor, benchmarking tools, and technology processes. I mean, there are the systems in place that we can utilize to measure in terms of performance. Managing leadership, taking advantage of all the skills. It's not just working with the process team, it's working across the maintenance team, the mill managers, even mine planning team, the mining team. And lastly, it's looking at systems and infrastructure. What are they capable of achieving now? and what systems we need to have in place to realize as we progress through just to medium to major capex projects. So I'll just go through a quick case study. This is the work we did at Penasquito. This paper was presented at the 2019 SAG conference. I can provide a copy of this, the paper after this presentation. I don't want to share anything new which has not been publicly available in the public domain. So I thought I'd share this because it largely talks about the methodology we undertook at Penasquito. So the summary of work, the major constraints are low throughput due to competent ore, extremely competent ore, underutilized comminution equipment, incorrect operating parameters, and there are some challenges with bulk ore handling. And the optimization period was end of 2018, and we did complete the work during COVID. I think it was about mid 2021. And through this period, our objective, we realized that we can increase throughput by 15% for the extremely competent feed, and we achieved that. Again, defining the value, and we built a combination met model using this. It's largely utilizes power-based modeling, and the backbone of this met model is power-based, but it has full-size distribution we can incorporate, which tracks the F80 and the P80 values for each stream. And we demonstrated value by building a met model, and we looked at the adjustments we needed to maximize. For example, it had a primary crusher feeding the SAG molds, and it also had a augmented circuit, which takes a portion of the feed from the coarser stockpile, sends through a second crusher, and the screen undersize feeds to the HPGR circuit. Now that gets combined with the primary crusher feed to the two SAG molds. The pebble crusher gets combination of the screen oversize from the secondary crusher, and that gets fed to the HPGR as well. But there are multiple options. You can bypass the HPGR. You can send second crusher feed directly to the SAG mill, or you can send SAG mill with crushed pebbles only. And the flexibility of this modeling work was allowing us to understand where the constraints and what opportunities, what the objectives should be going forward in terms of the debottlenecking project for the Penasquito work. So the analysis of the data, we looked at there was a second crusher and underutilized installed power. There were challenges to operate at high throughput with low cost height. The HPGR had it was a 5 megawatt unit, and when we started doing the work, it was only drawing less than a meg. So essentially, we need to maximize the power drawing HPGR to increase efficiency and circuit efficiency, rather. And what are the changes we need in terms of HPGR control strategy going forward? The SAG mills. We did a crash stop when we investigated. It was operating with high mill load, and there was an effective process control strategy around that, and poor inappropriate mill liner design, and as a result of that, there was poor control strategy in operation. And largely, I mean, the SAG mills were not fully utilized because it was not driven hard in terms of performance. Pebble crushers, there were 3 sandwich crushers. There were some opportunities around optimizing the bin level to effectively utilize the pebble crusher power to further improve the crush prior to feeding the SAG mill or the HPGR. So the analysis outcome, just to highlight here, I've got a picture of the plan view. So we got the coastal stockpile, HPG unit sitting in the middle here, the feed to the SAG molds. That's the location of the second crusher feeder. That's the second crusher tower. The product is sent to the product screen. The oversize gets combined with the pebble feed as the pebble crushers, and the pebble crusher product and the secondary crusher product screen undersize is fed to the HPG. So the objectives are to maintain high cost level and increase the pebble crusher feed capacity. Then we change the operating strategy from not just going from 2 crushers in operation with 1 standby, basically fully utilize the crushers to maximize efficiently the comminution circuit. We maximize the feed to the HPGR, which is also a function of maximizing feed to the secondary crusher. And the last point here, the SAG mold control, fully utilize the mill speed, optimize the mill load, and we made sure that there's a pathway to optimize the liner design, which was not suitable for this type of ore. So the implementation, so that's the total plant throughput over here, and it's a function of second crusher throughput through a series of trials, and we understood there's a linear relationship. So the max potential for that circuit was about 4,700 tons per hour, and that was an objective sustained. A part of that valuation, as I highlighted earlier, was looking at the HPGR control and the pebble crusher bin level control. This is before the change, and once he implemented the change with HPGR ore speed control, it stabilized it, stabilized the bin level, and therefore we can maximize throughput through the HPGR. This is a picture of the SAG mold when we did a crash stop. It was full, and that's the feed chute. And I think at the level to the feed chute was about 38% full. It was primarily driven by poor control, and also the liner design. What they used was they keep changing it was a bi-directional liner design. And so they have no understanding of what the load set point should be every time they change direction. And so what we did was went from a 14% ball charge with high filling, and we increased the ball charge because it's always very, very competent, low filling. We increased throughput, and we dropped the load set point, and then we had to reduce the mill speed because mill protection was not, particularly around the acoustics, was not properly calibrated. So we ran the mill slower, but we still achieved a higher throughput at a low power draw. So there's plenty of opportunities to push that circuit once you optimize the liner design in combination with the mill control with acoustics. So in closing, I'd like to leave with this thought from Jim Rohn. Success is 20% skills and 80% strategy. Largely what we do in my type of work and our type of work, I would say 20% of it is just, technically we know what the solution should be. 80% of the time, it's all about developing a plan, how we're going to execute that plan. And that has always been the challenge. And with that, thank you for listening.
Thank you, Rajiv, for the very nice presentation. So we have time for some questions. To ask a question, please raise the hand or open the mic and speak up. Any questions? Check here in the chat.
Perhaps I can ask people in the audience, I mean, how successful were the optimization, and has it been challenging with people management skills, um, and when you set out to trial increasing throughput through a SAG mill, what are the key challenges then? Question for Yannick.
Yeah, good morning, all. Thanks for the good presentation, Raj. The question is about the new technologies we're seeing with the twins for mineral processing, including the comminution. Do you believe it's going to help to debottleneck those process plants? Or because your first point was stabilize it, and if you are able to twin it, you should be able to stabilize it. So what do you think about it?
Yeah, yes, I mean, digital twins is another the type of simulation, the way I look at it. And so any input data for a digital twin, you need to make sure that the data is correct and it's calibrated. Now you can twin it, but if your measured inputs are incorrect, you will never know what the issues are going to be. I mean, there are clients you actively using digital twins, but my first step is your instrumentation properly calibrated, the key input data, what you're measuring is correct. And then once you understood that if the system is pretty well calibrated, then you can utilize an opportunity to debottleneck, understand where the constraints are.
Yeah, for sure. Because if you have a good twin, he's going to replicate what you're doing bad. So yeah, I see.
Yep.
Thank you.
Thank you. So, Professor Marcelo.
Yes, excellent presentation, Rajiv. Really nice to have a structured way to really look at this bottlenecking, because there's a lot of intuition behind it, but it's nice to really put in a nice structured way. My point is kind of an unusual one, which is, since you talked about skills and strategies, I was wondering, on your experience, how able you have seen operations to actually go through the process, for instance, with the support of you guys, to actually do this debottlenecking and analysis. And after you're gone, you go back to Canada, how well can they really uptake this? Because it is, in the end of the day, the process that we want to internalize in companies. But of course, we know a lot about turnover, a lot of lost memories there. I was just wondering, because you really had a track record.
Yeah, so that's a very good point. So the work we did at Penasquito, when we started that work with Goldcorp, this before the acquisition by Newmont. And the team at Goldcorp, very proactive. They are fully engaged. They had one of the guys who worked for Goldcorp at the time, Comminution, Kevin. Then he joined my team. But the guys were very engaged. They were pretty much driven, and that's how we were successful, to drive that change. And I've lost track of it once it sort of bought out by Newmont, and the company's got too big, and there are so many processes in place, and the key stakeholders who were driving and championing a lot of that work left. The last time I heard, I mean, I'm not sure if I forgot his name, the guy from Comminution, guy from Newmont. Is he Ben? I'm not sure Ben's in the call, but I mean, it's challenging to go back to the legacy work and what's been done. And yeah, like I said, the last point, 20% is easy stuff. What we do is, it's fundamental, it's well understood. 80% of the time, it's implementation, planning, seeing it through, and it's always been challenging. If you have a good team at site, it works well. If the team at site, they lack understanding and the objectives are not aligned with ours, is always going to be challenging. But it's all part of communication and aligning. Yeah, ultimately, I would like to see it through, and that's the just like you're saying yourself when you do consulting work. Yeah, when I do go back to some of the sites, yeah, people probably just go back to what they know and defer to. But yeah, it's always good to keep track of how things have been implemented and changed. But if you find champions at site, they'll make sure it's seen through.
Thanks, Rajiv. Yes, my experience has been that a few companies, few sites that we have worked with,
Yeah.
they after many years they asked me for the service, and then I said that,
Yeah.
oh, I'm sending you the report because it's going to be exactly the same last time.
Yeah.
So
Yeah. There was
sometimes
yeah.
it is sad,
Yeah.
isn't
There was
it?
yeah. I mean, there was a client in South America, and he asked me to come review the circuit. I did it, and I wrote the report. And they said, "Okay, can you come back a year later?" It was the same problem. I said, "Okay, go and read my report, which I wrote a year ago." So I don't want to waste the client's money. I said, "Well, I mean, it's the same problem. You just have to go and read and implement it. If they need help, then I'm happy to help implement it."
Yeah, absolutely. Thanks, Rajiv.
Right. Olga?
Yeah, thanks for the presentation, Rajiv, first. Very interesting. For me, the question is, I mean, we are discussing, particularly here in GCC, quite a bit about dynamic flow sheet simulation systems. What is your experience so far with dynamic flow sheet simulations versus the traditional one, which is essentially, okay, a mill has a certain throughput at certain conditions, it will generate certain products. What we find in many instances is essentially it's the non-stationary processes, transient processes in the systems, and you have nicely shown the transient situations in the SAG mills. It's these transient situations which determine the capacity of the circuit rather than the stationary. Essentially, you never have a stationary process.
Yeah. I would say, I mean, we have internally, we rarely use dynamic, I would say true dynamic simulators for optimization work. It's largely steady state type of work. Because it sort of gives you, assuming your system is stable, where your opportunities are. We're looking at the big picture, where the constraints are. Dynamic simulations were far more useful is when you're looking fine-tuning a control system. And if you have for example, advanced process, I mean, I used to have a process control specialist, but and they try and mimic the system by using in some transient, as you pointed out, as you change in or competency or density changes, or what that effect will have on the overall system. And that's when you start to look at from the, say, the dynamic type of simulations. But I mean, most of the time is where we use these, as I pointed out, the heat maps to identify where the opportunity, what we need to focus on, and we make those small incremental changes in the operating parameter and see how the control system reacts. Had we utilized a true dynamic system, then yeah, we should be able to model it. But then again, it goes to the point, how do we model a system if the instrumentation is not properly calibrated or properly tuned. So, so you need to understand how do we what's cause and effect. So yeah, so
I think what would you say about the impact of computer power? I mean, what we see here is to model a true transient situation, you have to consider a number of parameters, and you have to calculate. In particular, if you're looking at twinning a process, you have to be faster than the process itself to predict what happens in the next second or the next minute. And then to give advice to the controllers or to give recommendations, or maybe at a certain stage even to control the process in a certain direction. So you do a choice between the different alternative parameters which could happen or scenarios. But the computational power is still a bit limited, I would say. Or how do you see it?
Well, yeah, the key, I think the missing data in the overall system at this stage is for comminution characteristics input. If you have an online system, if you can measure feed density changes, I mean, we have particle size measurements, or competency changes, and feed that into a dynamic system, then you should be able to model any of the transient changes. But given that we are modeling, we are trying to model average ores coming into the system, and that's what you rely on steady state as the best guess.
Which is the first mistake already.
Yeah. I mean, look, I look at from how precise do you want the answer, or I rather focus on the accuracy rather than the precision. If you're there was a job I did in Laos. The ore was changes from its diorite to magnetite, so the density changes. But I mean, the client didn't have that density measurement, the ore density measurement, and so it was more relying on competency. So you can see as your system is, when you're doing high throughput with the diorite with fine material, and you get a feed of competent hard material, and then you get these big swings in stability. Yeah, very good advanced process control. And I said, okay, how can we track this change in ore density? We said, okay, we can track the truck dump. We can have an RFID sensor on the truck. As it comes to the coarse ore stockpile, then it loses that information. So you try and quantify it. Now you can put sensors on the conveyor belt, but you're still not going to have a precise or a far more accurate way of controlling the sag. What we did eventually was we installed a volumetric scanner on that sag mill feed conveyor. So you have a weightometer, you have a volumetric scanner, so you can infer an SG of the ore. So what we did was, instead of controlling the sag mill load or the water addition to the sag mill by weight, we controlled it by volume, and it stabilized the system. It was a simple system. So I mean, it was a Yokogawa advanced process control, and it worked well. And so instead of having input as a mill weight by tons, we control the mill water addition by volume.
By density. That's interesting. Thanks, Rajiv.
Thank you, Rajiv, for the questions again. And then if you have any other questions, the audience. Still have 5 minutes. Oh, I don't have it. Thank you again, Rajiv, for the very nice presentation and for being with us here today. Hope we can see you guys next month. The GCC student day. The invitation will be circulated shortly. So thank you very much.
Thanks, everyone. Thanks for listening.
Thank you. Have a good time.
Bye, Rajiv.
Thank you.
Very good job.
Bye, Rajiv.
Thank you. Interesting.